Okay, good afternoon, everyone. So we'll start the lecture from now onwards because it's the time now. I think you can remember we discussed about the composition of the mantle. That means the chemical composition of the mantle is a leusolite, right? Leusolite. That means composed of mainly orthopyroxene. Orthopyroxene, clinopyroxene, and olivine, right? So as this triangle depicts, you can clearly see the composition of the mantle is mainly mafic. Okay, so because all these are iron magnesium rich minerals. So out of those minerals, the majority of the mantle rocks are composed of this blue area. Okay, this blue area indicates the main composition of the mantle, which is in general we call leusolite composition. Okay, so the triangular area, the blue triangular area here, we call leusolite area. And as I mentioned, some of the in some of the situations, due to upwelling of the mantle, right? You know the upwelling. Mantle upwelling means the convection brings up the hot materials to the shallow level, right? So this may be some tens of kilometers, maybe sometimes it's like 100 meters, 100 kilometers, or sometimes it's 30, 40, 50 kilometers, like, right? If it is deep mantle material, then it should pass at least about 100 kilometers of the upper level until it reach the upper levels of the mantle. Okay, so anyway, when these materials are brought up, I mentioned that the mantle starts to melt, right? Mantle starts to melt when it comes up to the shallow levels. As I mentioned last time, there are two ways for the mantle to be melted. That means two mechanisms. Okay, you can increase the heat, right? You can increase the heat. That means increasing the temperature. Okay, that will cause obviously to melt the mantle. For example, if there is a bombardment of a mantle plume, right? The mantle plumes are coming from the deep part of the mantle. So if such a plume is coming up, plume means a very hot magma. Okay, it's very much hotter than the normal magma that is available at a volcano or at the source area of a volcano, right? So this mantle plume magma, which is coming from the core mantle boundary, very deep, some thousands of kilometers deep. Okay, so that hot magma can easily make the shallow level mantle materials to be melted, right? That is one way. The other possibility is when the convection currents are operating, these connective forces can take up some of the mantle materials to the shallow levels, and due to that, the pressure decrease occurs, right? Because the deep mantle, when it comes from deeper levels, for example, if it is coming from 40-50 kilometers below, then it can pass some another 20-30 kilometers to the shallow direction towards the upper mantle, right? So then there is a significant drop off of pressure. So that is what we call a decompression, right? So this decompression can cause decreasing pressure, and it can cause simply melting. So not only heating, but also decompression can also make mantle materials to be melted, right? So these are the main two mechanisms available in the mantle for making magma. So decompression melting is vigorously taking place at shallow mantle levels. That means in the upper mantle. Okay, so such magma brings up, they come up in conduits, making volcanoes on the surface, or in other words, extrusive eruptions, right? But in some cases, as you know, in your third year, you have learned intrusive rocks, right? So when such magma is not coming to the surface, they can recrystallize after gradual cooling within the crust itself. Such possibilities also there. Okay, but remember, at the shallow levels of the mantle, there is intense melting taking place due to decompression, right? So mantle convection drives all these melting process because they brings up more hot materials to the top levels, but as a result of sudden pressure change, this melting occurs, right? We will see how that happens in terms of phase diagram later on, but just keep in mind that these are the two possible mechanisms. Okay, so the leusolite composition is the main mantle composition because the majority of the mantle materials, that means the mantle rocks, are composed of this blue area composition. So this blue area belongs to peridotite composition. Okay, here you can see the peridotite composition. So that is the most of the mantle composition. But in some areas, there may be less olivine, less amount of olivine. For example, compositions like here, right, in this orange area, right? Some compositions prevailing in this orange area can also be found in the mantle, but not much in volume wise, but still possible. Okay, those we call pyroxenites. Okay, so but anyway, pyroxenites are not dominant in the mantle. They are available, but they are not dominant. What is dominant is peridotites. So the peridotic composition comes above this 40% olivine mark. Okay, this is 40% model percentage of olivine, right? So you know, along this axis, when you go towards the olivine, the composition increases, right? Model composition increases. But when you go down, olivine composition decreases, right? So olivine, around above 40% of olivine, always the mantle is composed of. So remember, minimum mantle composition for olivine is 40% of model composition. And at the same time, the melting takes place, as I mentioned before. During this melting, first to melt is clinopyroxene. Okay, clinopyroxene starts to melt first. So that means when you have a mantle, we call mantle parcel. Okay, mantle parcel. Normally we call them mantle parcels because they are the ones taken by convective forces towards the shallow level. Okay, so the convective forces are coming like this, bringing these mantle parcels upwards, as I mentioned before. So when they come up, what happens is there is a drastic pressure decrease. Okay, so there is a drastic pressure decrease. So due to this pressure decrease, as I said, this mantle material get melted. Okay, pressure, there is a pressure decrease. Okay, right. So this melting is not taking place as a complete melting process, right? It just melt only partially. So that's why we call partial melting. So partial melting means in a mantle mantle parcel, from place to place, you might observe some initiation of melting, right? It's not just melting at once, just initiation of drops of melts. There are several mechanisms of this aggregation of melting, which we will learn later on. But just I mentioned the names: batch melting and fractional melting. Okay, batch melting means these drops of melts come up or they are released as a batch of a melt, right? So it comes like a full batch of a melt, because they start melting, and somehow they are still be in equilibrium with the initial mantle parcel, but later on, once they get accumulated, start to flow upwards, percolate, right? That is batch melting. But there is another way. There are all these drops of melts, as soon as they are formed, they will escape, right? So like this, they can escape independently, separately. But later on, somewhere they will be pulled, and they will also form a conduit, melting conduit, and then they go up. Okay, this happens. But at the source region, only drops of melts are produced, and they are escaped separately. So this is called fractional melting. So batch melting and fractional melting are the two types of melting available in the mantle, in the Earth's mantle, right? So they produce very different compositions. That is the most important point. Although the initial composition of this mantle, say you have X composition, right? That produce some melt. Let's say its composition is F1. Okay, I mean this is Majan trace element compositions, right? I'm referring, and then the other mechanism will produce a melt from which has a composition F2. Okay, actually it might be say, okay, let's say this is XY, sorry, FY, because they are this batch after fractional melting is produced as a aggregation of these drops of melts, right? So that means each drops of melts will be having separate compositions, right? So they might be FA, FB, like that. Okay. So once they are get accumulated, they will be having a composition like Fy, right? So F1 here after what this is after batch melting is entirely different from Fy, although they are produced by same initial composition of the mantle, right? So they actually they they depend on their individual chemical affinities of each and every element, but the way they contribute into the melt is different from one to another. So that's why their composition is getting drastically different. So we will learn about these things later on in detail. Okay. So anyway, mantle melting takes place at the shallow levels of the mantle due to decompression mainly. And I said the first to melt is clinopyroxene. Okay, the first to melt in the sense we can say the first to contribute into the melt, right? For example, you have a CPX in the original mantle, right? You have CPX in the original mantle, and part of it will be contributed into the melt, right? It will not completely get melted, right? Say in your original mantle, like you had a composition, say like here, okay? So if you had a composition like that, so what would be your CPX composition? How can you find it? You can just make a line parallel to this axis, okay, these two lines, because CPX is lying here. So you need to draw a parallel line there and then find out what is the percentage here, percentage value, right? So that means this amount. Say it's 40. So normally this is 40. then we can say 45, 50, 55 or something, right? So something like that, right? It should be a graduated triangle. Then you can easily find out the exact composition. So that for 50, say 50, 50% model volume percentage of CPX will not be entirely contributed into the melt. Maybe 5% of that will be contributed. Okay, so that means in your melt, in the melt that was produced by this original mantle parcel, which had 50% of CPX, will contribute only 5% out of that into the complementary melt. Complementary melt means the produced melt from. Sorry, there was a disconnection. Do you hear me?
Yes.
You hear? You can hear? Yeah, you have the mic. Tell me. I think you can hear me, right?
Yes, sir.
Okay. Okay. So maybe 5% is contributed, right? That depends on how the melting. I mean the melting conditions, the background, and all, right? So we will learn about those how to calculate those contributions and all because there are some equations. So just keep in mind that they will not melt completely. And then next to melt is orthopyroxene, right? Orthopyroxene and then olivine. So that is the normal way of melting in the mantle. That is experimentally proven. Okay, so melting clinopyroxene first means you are reducing the clinopyroxene composition, right? You understand? If it is 50% at the beginning, then say 5% was contributed, then definitely it should indicate your original composition which was lying here should go like that. Okay, it should decrease. Decreasing means you are going away from this peak, this this corner, clinopyroxene cone, right, along this direction. And I said the next to melt is orthopyroxene. So say orthopyroxene was here in 30% or so, right? Just a number, right? Just a minute. Suppose you have orthopyroxene here. So how to calculate the orthopyroxene amount which is available here? Okay, I'll take another color. Here, how can you do that? You have to draw a line like that, right? Which should be parallel to this line. Okay, so which is opposite to the OPX corner, right? So when OPX is also contributed to the melting, contributed means consumed. Okay, they will get reduced, maybe 7% or something, right? Any percentage. There are maximum and minimum, not minimum, maximum limits there. We will talk about that later. But just keep in mind that, so you are reducing the orthopyroxene composition also. So if you are reducing the orthopyroxene composition means once this melting is taken place, your OPX composition should go this direction. Okay, so it should go in that direction because it is reducing, and you are reducing the olivine also at the same time. So what is the olivine composition? Olivine composition should come like this. Okay, so finally you are reducing olivine means your composition should be going which way? This way, right? So this is a little complicated process because everything does not does not get decreased in linear manner, right? They are not linearly decreasing. Therefore, this pattern you can't predict. You have to make some calculations for all these three minerals together, simultaneously, and then find out the final composition. But once you complete, there are formulas for that. We can use those formulas and find out what was the final composition. And then you will realize that the final composition of this mantle, when they are little by little getting melted, right? The CPX maybe a little more, OPX again little more, olivine is also contributing more. So then you will realize this trend will be like this, turning like that. Okay, so originally it was here, but little by little it's going there, because I said the the first to consume is clinopyroxene. So then it should reduce first. So clinopyroxene reducing means this way. Okay, clinopyroxene reducing means this way. So when clinopyroxene starts to melt, other minerals stay as they were without melting. So therefore, they will not move this way or that way. Okay, only CPX is getting reduced. So your final curve or the compression curve will be moving like that. And then starts orthopyroxene. So it reduces in this way, right? In this direction. So that means your curve should start to turn in a direction like that. Okay. So this curve should start to move or turn in a direction like that, because the system is losing orthopyroxene in this direction, right? So olivine also contributes, but remember, olivine contribution is the last, but it's also the least. It reduces only very little amount. So even you try to melt olivine a lot, it's very hard, and the contribution to from the olivine to the melt is very very minimum. So therefore, more or less, you don't see a shape change for this curve, this melting curve, due to olivine consumption. So therefore, normally in a melting mantle, you will see a curve like this direction changing. Okay, so that means from lazulite, then it reaches, what is this composition? H. I have covered everything with these lines. So this is the Harzbergite composition. Okay, remember Harzbergite. This field is called Harzbergite. That means up to 5% of CPX there, but majority is orthopyroxene and olivine, because in this region orthopyroxene is rich and olivine is rich. CPX is very minimum. So when CPX is almost over its consumption, OPX starts to melt. So therefore, it starts to turn like that by going to a field called Harzbergite, because reducing CPX means you are trending towards Harzbergite field. So you are trending towards like this. That means towards Harzbergite field, and you touch the Harzbergite field somewhere here, and then finally even the OPX is getting reduced because of its melting at the second stage. So it moves in a direction like that, and now olivine, CPX and OPX are removed from the system. I mean, not completely, but most of them have reduced. Then finally, and also olivine does not get melted much, as I said, right? It does not contribute to melting much. So that means you are removing of this triangle, you are removing CPX and OPX out. Then finally, what will be the enrichment? Olivine will get enriched, right? Because these two will be going away. So olivine composition will be getting high and high. So then what happens to this curve? So it starts from lazulite, and then it goes to Harzbergite here, somewhere here, and then reduce OPX also, and then finally what happens? It will become olivine rich. Olivine rich means this composition. What is that? Danite. So this rock or this mantle parcel finally become a dunite, dunitic rock, a dunite rock. Dunite rock means olivine rich rock. More than 90% of olivine is there in a dunitic rock, right? But always this does not happen in the nature. Of course, the dunite is formed, but this melting cannot continue up more than 30%, right? It's very hard to melt. So I mentioned here 5%, for example, that is just the starting. It can go increased up to 30% or so. And there onwards, there will be no melting because it's very hard, because you need more heat for further melting, right? But under normal decompression conditions driven by mantle convection, such high heat is not generated. Therefore, normally you can find majority of the mantle rocks as lersolites, and then Harzbergites, and then dunites. Okay, so the melting does not make 100% melting there. That's why, right? It needs a lot of energy, a lot of heat is required. In a place like mantle plume is there, then it's possible to melt and produce a very, very dunite rich mantle composition, right? But anyway, just keep in mind that this is the style of melting. Okay, this is the way of melting due to the heat, the responses to the heat of these different mantle minerals: cyanopyroxene, orthopyroxene, and olivine. In case if garnet was there, right, in some mantle, although garnet is not included in this triangle, right? Normally we don't include garnet in this triangle because it's a crustal mineral, but it can occur in the mantle also. But we are not specifying mantle composition in terms of garnet contribution. In case if garnet is there, then what we how we classify the rock is we make it as a kind of adjective like, right? Garnet lersolite, garnet Harzbergite, right? Or we don't normally say garnet dunite, but we say garnet bearing dunite. But those are very, very, very rare, right? Garnet bearing dunites, right? It's very, very hard to find such mantle rocks. But garnet lersolite, garnet Harzbergite can be found. Okay, but still, if the garnet is there, that indicates more deeper levels of the mantle. So this is how the mantle melting is taking place. And if you consider the composition of the mantle and also their each mineral's contribution to the mantle melting priority. So heat is very important. Enthalpy is very important to increase their melting condition, to make their melting contributions to the formed melt, right? So I said here not the complete melting is taking place. What is happening is partial melting, right? So if this is partial melting, then what happens to this solid, right? So you had originally the mantle here, mantle parcel, which due to decompression started to melt. So that means some components were lost. So that such lost components are moving with the melt like this, or like this, fractional melts or batch melts. So what happens to this, the remaining portion? It is still remaining there as a solid. Remember, it should be remaining there as a solid because you just only contributed some portion of melting there, right? So it's like we are burning some firewood and produce charcoal, right? So this is a residue, right? This is what we call a residue, right? So this residue is more enriched in either orthopyroxene or olivine, right? Because I said CPX is more vulnerable for melting, and it is more enriched in the melt. So you are getting a reduced concentration of CPX or model percentage of CPX there. So that means you have automatically increased orthopyroxene and olivine compositions compared to the initial mantle passer. So we call this as a residue, right? Melting residue. So as a result of partial melting of the mantle, we have two products. We have a melt produced and a residue, right? Melt and a residue. So their compositions are very different because some elements prefer more towards to be partitioned or to be moved into melt. Some elements prefer to stay in the solid. So based on such properties of elements, that means these are chemical properties, okay, of mainly major and trace elements, specifically trace elements. Major elements also has such behavior, but mostly we can identify very characteristic changes in trace elements. So some elements prefer melt than solid. Some elements prefer solid than melt. So based on that, you will get a very different composition from the melt and the residue. Okay, so this is a basic concept of mantle melting, and I think you could understand of this principle. And of course, there are some other complicated types of melting also. That is what we call uh, aggregate melting, and yeah, that is one complicated type of melting. Okay, so aggregate melting is also different from the fractional melting, which the details you don't need at this stage or at this level, right? If you do postgraduate, then you will have to learn at that level. Okay, so anyway, just keep in mind this is how the mantle melts. Any question regarding this mantle melting, mantle composition and mantle melting? If anything you did not understand, you have the mic, you can talk. If anyone has, because this is not this is not very kind of familiar to us at your level. So but you need to read this stuff to get more well digested. Okay, so you have to use, I always say this, you have to read a book, okay, rather than just googling, because in textbook you get everything systematically, right? If you miss something, you can find it in the internet, but normally this type of concept should be well understood, right, as final degree student, final year students. Okay, right. So I mentioned that some garnet bearing mantle compositions may be found in very deep levels. So you can see here garnet above 80 kilometer, right? Normally above 80 kilometer depth garnet occurs. And we have another mineral, although it is not included in this triangle, right? Like garnet. Garnet was not included here. And at the same time, spinel is also not included. But spinel is a very common mineral in the mantle. So that means in peridotite, you must have spinel. Although we are not taking its model percentage to classify the mantle rock, right? Okay, right. So spinel. So if you have spinel in the mantle composition, or if you have garnet, then you can use it as a adjective or prefix for naming the rock. For example, garnet leusolite, garnet spinel leusolite, even plagioclase, right? Plagioclase leusolite. But plagioclase leusolites are not very common. They are because they are shallow, right? They are very shallow. That means less than 30 kilometers. But remember, all these three phases, all these three minerals represent aluminium bearing composition, right? We call it aluminium bearing phase, aluminium bearing phase in the mantle. That's why actually we don't take that into classification, because by definition, the mantle is composed of magnesium, iron magnesium rich minerals, right? We don't say it's rich in aluminium rich minerals, because aluminium is rich in the crust, right? But these minerals occur in the mantle, so therefore we have to use them when they are classified. But for the classification, we base these three main minerals, iron magnesium minerals. Okay, so I think we have discussed about the evidence for this mantle. You can see here on the slide, we have ophiolites, right? So ophiolites means slabs of oceanic crust and upper mantle. That means both upper mantle and oceanic crust together thrusted onto the continental crust, right? This is not very common. The reason is, you know already, oceanic crust is heavy, right? Oceanic crust is normally heavy. So that means when you meet, when a continental crust meet an oceanic crust, what happens? Oceanic crust tend to subduct. Therefore, naturally, you can't find oceanic crust on the crust. But there are some situations where some tectonically emplaced, not only the oceanic crust, but also together with the upper part of the upper mantle. That means the lithosphere, right? Lithospheric thrusting onto the crust is called ophiolites. In Oman, there are very popular or very famous ophiolite, which is widely being studied by all over the world people, scientists. So that's a very good location to see ophiolite. So there you can find some parts of the upper mantle, because the upper mantle has come onto the continental crust. Very rare occasion. Otherwise, we have to drill, or we have to try to find a way to go to the mantle, right, to get a sample. But here, naturally, it has come onto the surface. Then we call it abduction, not subduction, but abduction, because it's kind of opposite, onto edge of continent at convergence zones, right? So it's not subduction, but we call it abduction. And then we can have dredge samples from oceanic fracture zones. Dredge samples means you can drill ocean floor, right? You can't start drilling from the continental crust to the mantle. It's very deep, right? 10 15 kilometers you can't drill. But if you go to the oceanic crust, oceanic crust is not very thick. So oceanic crust can be drilled in some places where some fractures are present. So through these, inside in these fractures, you can find some mantle components, mantle rocks. So you can dredge them, you can take them out there. So we call abyssal peridiotites. These are called abyssal peridiotites. Okay. So abyssal means ocean floor. We call it ocean floor peridiotites or abyssal peridiotites. So ophiolite is one instance that we have a mantle sample, and this abyssal peridotite is the second opportunity. And we have another one that we call orogenic massifs, right? Orogenic massifs or alpine type ultramafic complexes, or orogenic peridotite massifs, or another way, alpine type peridotite complexes, right? So this alpine type means there is in the alpine region, Italian alpine region, this type of peridotites discovered. So therefore, this term has come up since many years ago. But these are called orogenic also, because they are like collisional zones. Like normally we refer orogenic zones as mountain building areas, right? As a result of continent collision, right? So similar kind of a minor tectonic activity has taken place in some areas when the subduction almost ends, right? So in a subduction zone, sometimes these mantle materials have come up and formed a massive or mountain, right? So these are big, big mantle components, big mantle areas. You can find very big samples, right? Like ophiolites. Ophiolites also you can find large samples, some big layers, some kilometer scale layers, right? Here also the same, right? Very large areas of mantle can be exposed in orogenic petrolite massifs. And there is another opportunity for us that is called nodules and xenoliths in some basalts. So nodules mean some pieces, and xenoliths are also like entrapped portions of mantle, right? So entrapped means when you have a basalt, right? So basalt is coming up, it's flowing, it's a liquid like here, melt. So it carries some fragments of mantle, right? Some small pieces of mantle. You can find some olivine rich, very greenish, very beautiful fragments, rock fragments. Okay. So they are called xenoliths and also nodules, sometimes called. Right. So these are sometimes very small, some millimeter scale or centimeter scale, but still they are mantle samples, therefore very precious because you can't access the mantle easily. So this is another way of getting mantle samples. And we have another possibility, that is kimberlite xenoliths, right? The same type of xenoliths, but brought by kimberlites. So, you know, kimberlites are coming from more deeper levels, but not as deep as mantle plumes. But these kimberlites like pipe-like intrusions up to the shallow levels of even up to the crust. You know, from the deep, in the deep mantle, there are diamonds, right? So these kimberlites are bringing up diamonds with them because they are coming from very deep regions. So that's why in Africa, many African countries, you have a lot of diamonds coming up or taken up by these kimberlites. Okay. And these kimberlites can also bring some xenoliths as basalts. Here you get those from basalts, but here you get from kimberlites. So actually, both kimberlites and basalts are anyway magma, right? But their chemistry is different because they are generated or originated from different regions of the mantle, right? So anyway, they also can bring up some mantle xenoliths. So we call these pipe-like intrusions, right? Huge, big, quickly intruded from the deep mantle, carrying numerous xenoliths. So they can also bring xenoliths, small fragments. So we have ophiolites, abyssal petrolites, orogenic massifs, xenoliths as the samples from the mantle, because the mantle is inaccessible. Unlike the crust, we can find anywhere samples easily, but mantle is not easily accessible. So therefore, some passive processes like these, not the exact active processes. That means we can't drill and get mantle sample, right? So some passive mechanisms should be utilized to get these samples. But we have advantages and disadvantages in each of these types of samples. For example, ophiolites. These ophiolites, although they are like some kilometer scale, as I said, they are highly altered. They are also, I mean, they are altered due to exposure on the surface. So they are easily altered, and also there are other types of rocks intercalated there, like pillow lava, basalts, gabbros, like so they have sometimes reacted. The mantle, the portions have reacted with these gabbroic melts or some other hydrothermal solutions or like that. So therefore, you can't get the pristine composition of the mantle. So you can't get the original composition of the mantle from ophiolites, but there are preserved areas. You have to find it with an effort. Okay. So it is one disadvantage, although they are offering us a huge scale of sampling area. The abyssal petrolites, again, they are highly altered. They are very much altered even than ophiolites, because they are found in ocean floor. So ocean floor is always having these hydrothermal activities and a lot of chemical reactions taking place. So therefore, you can't find at least, like more than 90% of these abyssal petrolites are not useful for geochemical studies. So that is another disadvantage of those. But orogenic massives are very offering us very fresh samples, because they are like mountain-like samples, occurrences. But on the top, maybe some altered samples are there, but like in the crust, we can find a lot of fresh uh, mantle material. So therefore, these orogenic massives are the best to study about mantle, because they are offering some kilometer scale spatial distributions of those samples, as well as they are unaltered, they are fresh. And all the other xenoliths, sorry, I forgot to mention about the xenoliths. Xenoliths are also having some problems. What are the problems with xenoliths? They are always carried by basalts. So basalt means always a changing liquid, right? The melt, because when it is coming from deep to the upper levels, mineral fractionation is taking place. Once mineral fractionation is taking place, means you are changing the composition of the magma. So with the different compositions at different levels, these mantle materials will have melt rock reactions. So therefore, kimberlites or basaltic xenoliths are again showing some modifications. But still, you can find unaltered xenoliths. But still, we cannot guarantee that they are fresh, showing the pristine mantle composition. So that is also a problem. So in that case, these orogenic massives provide us a very good opportunity to study about the Earth's mantle, right? Petrology and geochemistry of the Earth's mantle. Okay, so that's about the Earth's mantle and its melting conditions. So you can ask me any question now. I think you have to interact, otherwise it's very hard to understand also whether you get digested the materials. Okay, so I have to leave out this portion, just a minute. Okay, so we discussed about the mantle composition, and we talked about the partial melting, right? So when you have the partial melting, you basically produce a melt, right? You basically produce a melt, and then you have a residual portion. So this is called residuum, or sometimes, most of the time it's called residue, residue, residue. Okay, or otherwise you can call it residual mantle also, right? No problem. So always remember, this residue has its complementary melt. So that means you had the original mantle which was not melted before, and once it gets decompression, or if it's get heated, then it will start to produce some melt, right? That melt will escape, and you are remain with the kind of a residue, right? So this residue is here, lying here. Right? Always remember why we are putting this residue down, because in this diagram you have aluminium, right? So aluminium prefers the melt, right? So most of the aluminium will be going into the melt. So melt will be enriched in aluminium, the residue will be depleted in aluminum. So therefore, it should go down. Right? Titanium is also same. Titanium, the melt takes much of the titanium, whereas the residue gets a lesser amount. Right? So its composition changes from the original composition, which was here. Okay. So now, say it melted different degrees. Say in this case it's 20%, but you can see the composition changes like that. So if you take it in the triangle, you will see a change of like this, right? Curve change like that. So it will, the original here also laser light, right? Here also laser light, because you see the laser light composition is broad. So little melted means somewhere here. So it is still laser light. Again, still laser light. And then it enters Harsbergite field. So that's why it comes here, Harsbergite. And then finally, it goes to dunite composition at the end of the melting. Right? So this is how the mantle melts. And if you consider the melt composition, you get a melt called tholeiitic basalt. We call it tholeiitic basalt. That means it's rich in aluminum and titanium compositions. We call it tholeiitic basalt, right? Normally, this melting, what we discussed, is taking place in a mid-ocean ridge, right? You know the mid-ocean ridge, where you have a spreading center. So how this spreading center is formed? Because of mantle upwelling or convection, right? So the mantle passes are bringing or brought up, and they start to melt here due to decompression, right? So this melt come up and dump in the ocean floor. Okay, they are dumped in the ocean floor. So this is what you call mid-ocean ridge basalt, MORB. We call MORB, MORB. So this melt produced is called a MORB melt, right? Mid-ocean ridge basaltic melt, because this is a mid-ocean ridge setting. Okay, this is a spreading center, because one plate is moving this way, oceanic plates, the other plate is moving that way, right? So the mantle pushes upwards everything. So melting is, so we call this region as a melting wedge, because this melting is predominant in like here. Okay, in this area you can consider as a wedge or a triangular region. In this part, a lot of melting is taking place, and gradually it ends up decreasing, right? So that means somewhere here, where this mantle convection brings the material just below the ocean floor, shows a lot of melting. Okay, then little by little it reduces, but the produced melt is coming up. Okay. So we are not talking much about pyroxenites here, because it's just a mafic rock, ultramafic rock, containing CPX, OPX, and olivine, but it's not a main part of the mantle. But still, you have such pyroxenites available associated with petrotides in the mantle region. So that means if you go to ophiolite, or if you go to orogenic petrotite, or even basalt that carried some xenoliths, might contain pyroxenites also. Okay, so they are there in the mantle anyway, but they are not composing the predominant composition of the mantle, right? So we do not take much into consideration here. So anyway, just for you, for your knowledge, you can classify the pyroxenites into Websterite and Wehrlites. Okay, Websterite and Wehrlite. So sometimes if the olivine percentage is higher, then you can call it olivine Websterite, right? The typical pyroxenites are depleted in olivine. That means they are pure Websterite or Wehrlite. Okay, so they are found as associated intrusions in the petrolites. Okay, right. Now we'll see a phase diagram in terms of the pressure and temperature in two axes, right? Sorry. You have depth also. And the normal geotherm is here. So the normal continental geotherm, right? You can see the geotherm here. That means that is the normal temperature distribution with the depth. Okay. So if you can, for example, say this is a 15 gigapascal. So it's very deep, right? You can see the correspondent depth is more than 400 kilometers. It's very deep. So that is the places where kimberlite magmas are coming up. But if you take the more mid-ocean ridge basalts, they are coming very low levels, right? Here, somewhere like here, even less than 100 kilometers shallow. So the normal magma that we have in volcanoes, erupted volcanoes, all produced in these type of shallow area, right? Up to 100 kilometers or so. But kimberlites are coming from deep regions like here, the diamond stability field, and what do you call the plume magma, mantle plumes are coming even deeper there, right? Not 600, 700, they can go up to even 1,000, 2,000 kilometers, right? You know the radius of the earth, right? So core mantle boundary, check the depth of the core mantle boundary. So that's why they are very hot. They are very hot, and also they are coming from very highly compressed areas, because they are, you see, the 20 gigapascal means huge pressure. The pressure exerted at a 600 kilometer depth is enormous. So that magma is coming with a very hot, and also with a large moving force. That means like momentum. Momentum is very large. So that's why it can hit on the crust and breaks into continents into pieces, right? Supercontinents are formed due to hitting of these mantle plumes, right? Sorry, supercontinents are broken, right? Gondwana broke because of a mantle plume. Rodinia broke because of a mantle plume, like that. So that's why. Okay. And you can see the garnet stability field is here, like above 100 or 80 kilometers, up to 100, like. And then you have high pressure phases down there. High pressure phases means the normal minerals that we have, normal silicate minerals that we have, cannot stay as it is at deep levels. So some of these minerals, including garnet, olivine, even quartz, they all change into high pressure varieties so that they can resist the pressure. Okay, they can resist the pressure. Do you hear me well? Do you hear me well?
Yes, sir.
Okay. So these high pressure phases are existing in deeper levels, right? That is another subject. So we call high pressure mineral physics. You don't have to touch that now. And also experimental petrology. Under experimental petrology, you can study in detail about these high pressure phases and how they change, and what are the requirements and all. Okay. So we have garnet, spinel. Spinel is here. and plagioclase at very shallow levels. So see how shallow they are. Plagioclase spinel, they are residing in very, very shallow levels. Even garnet is there up to 100 kilometers or something, right? Most of the melting in the mantle is happening in this region, okay, like up to 50-60 kilometers depth, right? Because presence of garnet in the mantle means you need huge amount of heat to make that mantle material into melts fraction, right? Even for partial melting, you can't easily do. You need a lot of force, a lot of energy, not force, energy, right? Enthalpy is very, very large there. So vigorous melting, which produce basalts, are taking place in this shallow level, right? Okay, so under normal geothermal conditions, you can see the geotherm here. Here you can see the geotherm, and you don't see any melt can be produced under these normal conditions. Under these normal conditions means along this geotherm, along this. How can I show you? Along this geotherm, there is no way of melting. Okay, it's just the temperature increase only. Nothing happens other than that, right? Just you are increasing the temperature with the depth, but no partial melting is taking place. So that means under normal geothermal conditions, you cannot melt the mantle. Okay, so that is the normal conditions. But how if we want to get it to melt? How can we do that? So we need additional heating, obviously, right? So geothermal condition or the geotherm is not enough for the mantle to melt, right? Even at 400 kilometer level, you have unmolten material, normal petrolite without melting. But if you want to melt this, say you have the petrolite here in this spot, right? If you want to melt this petrolite, you need to increase its temperature until it meets the liquidus. Okay, this is the liquidus of the mantle. Liquidus. So what is liquidus in any material? That is the critical temperature that a solid can stays as a solid, right? Beyond that, it will form into a melt, right? So here you have the mantle melt. The mantle as a solid. But if you want to melt this, what you have to do? You need to increase the temperature of this material so that it can reach here. So that means if your mantle material can hit the liquidus temperature, right? Liquidus temperature means this, and in this specific case, right? This is the liquidus temperature for this particular mantle. Okay, so if you can increase the temperature, because the current temperature is somewhere here, right? It's not the liquidus temperature at this depth, right? Remember, it's not just the temperature, pressure also, that means the depth also, right? So at this depth, to melt this mantle, you need to increase the temperature up to here. So see how much you have to increase. Maybe this is 1500, 1800 or something, and then you have to increase it up to 2200 or so, right? So from 1800 to 2000, from 1800 to 2400 means you need to increase temperature like how much? 600 degrees. Can you do that? Even the temperature around a depth of 10-15 kilometers is 600 degrees, right? So that's why we say that it's very, very hard to melt the deeper mantle. So deeper mantle means some mantle materials which are having garnet-like phases. Even here, garnet also not there. More high pressure phases are there. So it's almost impossible. You can't increase the temperature up to that much. under normal circumstances. But probably if you hit a plume there, right? The plume, coming from the core mantle boundary, and it carries huge amount of heat. It might help to increase the temperature here. So then this mantle can be melted. Okay. Otherwise, you have to find a way for this mantle to melt. So what is the other possibility of this mantle material which is lying here to be melted? But to tell you the truth, you can't melt this mantle material in any means unless you have a plume, right? Because you see, it's a 400-kilometer depth, so it is not realistic, but I am just taking it as an example. But you can consider some mantle material which is available somewhere here, maybe okay, right? So, but still, you see how much you have to increase the temperature. Sorry, until it meets up to here, right? So it's say 1100, and maybe this is 200, but still you see it's 900-degree difference. It's almost impossible, right? Unless you hit it with a plume. Okay, but just for the teaching purpose or for the learning purpose, we will take that somehow you can increase the temperature, right? So then you can make this mantle melted. Okay, so that is a plume heat. Otherwise, what is the possibility for you to do this very easily? I said there are two ways for mantle melting. What is the first one? Increasing the temperature. What is the other one? Decreasing the pressure. Remember, decompression, decreasing the pressure. So how can you do that? So if you happen to take this mantle material upwards like that, what happens? You can see it can still hit the liquidus, right? Here you try to hit the liquidus by increasing the temperature. So then you started melting. But since you can't find such a heat source, here what you do is you take it to shallow level, right? You take it shallow level until it hits the liquidus. Now you can start melting. So that is what you call the decompression melting. So remember, this is how the mantle can melt due to reducing pressure conditions. So always you don't need to heat the mantle to melt. You can just decrease the pressure without cooling it. I mean, you can keep it isothermal conditions without temperature drop, but you can just decompress it until it hits the liquidus. All right. So this is another way of the melting. So this is what we call the decompression melting. So what is why I said most of the mantle is melted due to decompressional heating, decompressional forces. So these forces are activated on the mantle by convective currents, right? So these convective currents carries these deep mantle materials to shallow levels. So as long as they can survive hitting the liquidus, they can survive without melting, right? But whenever it hits at shallow level with the liquidus, liquidus point, liquidus or solidus, both stay together, okay? Solidus means from there onwards, the material is solid. From there onwards, liquidus means the material is liquid. So solid liquidus line, or you can call solidus or liquidus, anyway, whatever, it's all right. Right? But since we are producing melt, we prefer to say it's liquidus because we are producing the melt. We are not crystallizing. So when you crystallize the material, then you can call it solidus, right? Because our end product is not the solid here in this case. Our end product is a melt. So therefore, better to use liquidus. So when it hits the liquidus, it starts to melt. Okay, so this is how the mantle starts to melt. So you can, I think, easily find how it can start melting by decompression. So this is the way the mantle get started with melting. Okay. So one way is increasing temperature that we already talked, which is the mantle plume. Okay, the mantle plume. Or otherwise, you can decrease. Okay, just a minute. Plume influenced geotherm. What happens to the geotherm once you heat with the plume? So if you are taking a plume here from co-mantle boundary, the normal geotherm will be shifted, right? Normal geotherm will be shifted towards the higher temperature sites. So therefore, the mantle material which is associated with the geotherm can be melted. So there you can see clearly some areas the melting can start, right? If the geotherm just hit the liquidus temperature and not exceed that, then of course you don't see any melting produced. Just the equilibrium conditions will be there. But if you exceed that, like here, definitely a melt component will be formed, right? So still you see the fraction of melt is produced there, and it can come up to the shallow level. Okay, so here you can see the rising plume. We call plume head and plume tail. This is the head. This is plume head and this is plume tail, right? It is coming from co-mantle boundary, very deep part, not 300, very below that. So that can carry the newly produced melt up there as we call hotspot volcanic activity. For example, Hawaiian Islands are produced as a result of this type of melting. Okay, so increasing temperature is one way, and the other way is decreasing pressure, right? So I explained it already. You have the decreasing pressure. That means rise of the mantle. That means the mantle materials are taken up, rising upwards like this with the mantle convection, right? So this is a passive movement because the mantle itself cannot come up, but it is brought up by these convection forces. So therefore, it's a passive upwelling. We call it adiabatic upwelling. Adiabatic means decreasing the pressure. So there you see the melting region, the zone of melting is taking place there. A lot of melting is taking place in this area, and then finally it reduces into like that, right? So the inverted triangle shows the vigorous melting area, and the normal triangle shows the almost the ending zone of the melting. So we call zone of accumulation because a lot of melt produced will be accumulated there, and then only they get erupted later on, right? So it's like chambers, like magma chambers, like. So see what happens in the adiabatic rise of the mantle. That means this mantle, which was solid, is brought up adiabatically, and it hits the liquidus, right? It hits the solidus and liquidus, the area zone, and then the melt is produced, starting melting. So it can continue melting up to this point. Okay. I think you can understand this process, right? Is there any clarifications you want more? Is there anything you want to further elaborate? You better draw this as a sketch showing the melting region, and also the liquidus and the solidus and geotherm, and you can mark with the arrows how it can happen. Okay, you can sketch this as well. Okay, the normal dry mantle is like this. That means in a place where you have very anhydrous phases there, right? Even no amphiboles or no biotite like anhydrous mantle, the solidus and liquidus conditions will be like this. But this dry mantle, you can start melting without much effort if you add some volatiles or water into this mantle, right? So if you add some drops of water into the system, then make it saturated with water gradually, then what happens is all these solidus and liquidus will be moving drastically to shallow levels, to shallow temperatures. Okay, so this can happen in subduction zones, right? Because in subduction zones, you know, there are a lot of hydrous materials are taken with the subducting slab. So when they reach the mantle, where the dry mantle conditions are prevailing, the mantle melting will be very, very vigorous. For example, if you have a subduction zone like this, right? Say one slab is subducting like this. Okay, one slab is subducting, and this carries a lot of sediments also, right? So sediments and some other materials, some fractions of the crustal components, because the oceanic crust can contain a lot of hydrous minerals. They are taken up by this subducting slab downwards. And what happens to these dry areas? Here you have very dry areas because there are no hydrous minerals in the mantle, right? You have olivine, pyroxene, and spinel garnet-like minerals, right? So when you bring these hydrous materials, they get dehydrated, and because increasing temperature conditions, and this dehydration cause drops of melts to go down into the mantle, right? So that means you are adding water. You are adding water into the mantle. So what happens is once you get this water saturated in this area, suddenly this solidus and liquidus temperatures drop. So as soon as they drop the liquidus point, this area can start melting. Okay, so they will produce some melted materials, right? So in subduction zones, this can happen easily. So in this way, it's also possible. So you know the water content of the mantle typically is about 0.2%, very less amount, very little amount. And some of the water in this region, even in these shallow levels, if some hydrous minerals are there, they are locked into the phases, those phases like amphibole or phlogopite or biotite, whatever, right? So as soon as they reach a little bit deeper, they dehydrate and release that water into the dry mantle. So easily the temperature can be shifted in this way, so that mantle melting can take place. So melting of the mantle can be enhanced by this way, by dropping the liquidus temperature. Previously, we had a situation where you cannot heat the material up to the liquidus temperature, right? Because whatever, if we want to whatever the region in the mantle, if you want to start melting, you need to increase the temperature so that it hits with the liquidus or solidus region, okay, in this region, combined region. But it is very hard. So what you can do is, now you are taking these liquidus and solidus temperatures downwards by adding some water, doing the opposite, right? Still the same thing happens, right? Then you can make it hit with the geotherm so that the melting can start. So this is another alternative way of melting, but actually this is not everywhere possible. In the extreme upper region of a subduction zone can happen, but in a mid-ocean ridge like this, this never happens unless you have other liquids like hydrothermal liquids penetrating in this region, right? So this is another way to start melting in the mantle. Okay, so remember the composition of the mantle and the mechanisms of partial melting and what are the products of melting, which we discussed previously, right? And how this melting initiates and what are the phases first start to melt, and then how they can change, I mean the pattern like this, right, from leusolite to Harsbergite to dunite. Actually this is this curve corresponds to the residual mantle. Okay, so that means the residue, because the melt is already escaped from the system and it is a basalt. So it's a tholeiitic basalt preliminary basically, but the residue changes in this way because of this style of melting, right? And then we talked about the temperature, how that the melting can initiate, considering the solidus and liquidus conditions. And also we talked about the adiabatic upwelling of the mantle, which also cause the mantle melting due to pressure decrease, right? This is almost isothermal. So therefore, it's we call it adiabatic upwelling or adiabatic rise of the mantle, causing the enormous amount of melting. So most of the melting in the mantle is due to this process, adiabatic decompression. Okay. Right. So here you also need to know, since we talk about the solidus temperature, so sometimes we use the terms called subsolidus and above solidus. So always remember subsolidus means it has not reached melting, right? It's still solid conditions. So it has not exceeded the solidus, subsolidus. If you have exceeded the solidus, that means supersolidus or above solidus. So there, you always talk about a melt, right? Under subsolidus conditions, you don't talk about a melt, right? All solid state changes can take place under subsolidus conditions, but under supersolidus conditions, liquid phases can be available, and also some liquid related processes like fractional crystallization or similar type of phase changes, cumulate type formation, like things can happen. We talked about the adiabatic decompression, which is the most predominant type of melting available, and also we talked about how to decrease the solidus and liquidus temperatures in the mantle. There we considered introducing volatiles or water into the mantle area. There you can decrease the solidus and liquidus temperatures significantly downwards, so that you can initiate easily mantle melting at a lesser amount of heat. Okay, I think I will stop here for today, and please don't forget the the attendance, to sign the attendance sheets, because I need to collect them all to see your attendance, right? So submit it to the office if you have completed signing. Okay, so let me finish today, then we will meet next time.